All right, welcome everybody. This week we're going to be talking about chapter 17 from the book we've been reading, Understanding Deep Learning. Uh, this chapter is about variational autoencoders, and so we're halfway through these 4 chapters on generative models. But I will say that this chapter and the next one gets much more mathy than the last two. So I'm going to go through the math, cover most of it, but fairly quickly. So definitely feel free to raise your hand, ask questions. I've been able to monitor the chat as well the last couple weeks, even though I'm on a single screen. But worst case, if you put something in the chat and I don't seem to see it, feel free to either unmute or raise your hand in Zoom. All right. So with that, let me go ahead and get started. So this chapter on VAEs, what we're going to do is by the end of the chapter, we're going to end up building a nonlinear latent variable model. And we're going to use an autoencoder architecture. We're going to do some sampling, and instead of being able to directly calculate the likelihood, we're going to estimate a lower bound, and we're going to try and get as good a lower bound as possible. So you can see here the different sections in this chapter, and it's a little bit sort of like, it's good that we get all the building blocks, okay? But what I found is it's a little bit unclear where we're going with these building blocks until you get to the end. You're like, oh, that's why you told me about all of these things. So so here's just like a high-level roadmap overview of where we're going, okay? So we want a latent variable model, and to have something more complex, we're going to use a neural network to do this, okay? We're not just going to have something simple like a linear model. But you cannot do maximum likelihood training on this in a straightforward way. It's just computationally intractable. So we're going to use a series of tricks, and that's what the first few sections are. It's building up this set of tricks that we're going to need in our toolbox, okay? So one of the things we're going to do is we're going to have a lower bound for the likelihood, and we're going to parameterize that lower bound. So once again, we can use gradient descent to tweak that to hopefully get as tight of a lower bound so that it's, for all intents and purposes, identical to the likelihood that we want to maximize. But even then, once we have this formula for an ELBO, we're going to find out that we can't really do it. So we need to do another level of approximation. We need to do some data sampling. And then finally, there'll be this small little reparameterization trick we need in order to do gradient descent. So these are all the little building blocks that we're going to have. And when we end up, what you're going to see is we're going to have 2 neural networks. We're going to have 2 main functions. One of them, we can use the familiar term, we'll call it an encoder. And one of them we'll call a decoder. And so anytime you have an encoder and decoder, then we've called these autoencoders in the past. But this is very different from a vanilla autoencoder, because a vanilla autoencoder, let's say you do one for images, you put the images in, and you will get in the middle of it, you will get an embedding. But you will have a single embedding, and this is a deterministic function. You put the same image in, and every single time you will get this one embedding. You can't do generation from this type of model because you just have this one-to-one relationship. So you put in one particular latent, and you only get one image. So it's not particularly useful for that. So in the VAEs that we're going to be building in this chapter, what you get in the middle is a distribution instead of just a single fixed deterministic latent. And so with this distribution, that means you can sample from the distribution and you can get a variety of things. And so again, we're not talking about like text to image, but like, you know, the simple example is if you had text image and you said a Siamese cat, it would be kind of disappointing if every time you got the exact same Siamese cat. You really want a model that you can say a Siamese cat, and you can give it different random number generators and different random seeds, and it'll generate a whole variety. And maybe you get 10 of them, and you're like, oh, I don't like the first few, but yeah. That 7th one, that's kind of what I was hoping for. So that's just the high level roadmap. And so with that, now we're going to kind of dive into the building blocks and the math of what we need. So the chapter starts talking about what is a latent variable model. So I kind of glossed over that in my intro. So we have some probability distribution we'd like. So let's just imagine it's like realistic pictures of cats. Okay, so that's our probability distribution over X. But instead of directly pursuing that, we're going to model a joint distribution on X and some other random variable Z. And this latent variable Z is unobserved. And so I just want to comment at a high level that, like, as humans, we do this all the time. So if somebody asked you to draw a cat, you might say, like, oh, well, is it a long hair or short hair cat? What color eyes does it have? Those theoretically are latent variables. Okay, you're not going to say, what is the pixel 200 comma 500 intensity? That's not the way we think. We're thinking in terms of much sort of higher level latents, right? And so it tends to be, for most real world problems, this is useful. Like, you can have a much more lower dimensional latent variable that describes things conceptually. So if you have a joint distribution on X and Z, you can find the original distribution probability of X by marginalizing out Z. And so the way you do this is you just integrate over, assuming Z is continuous, you integrate over all possible values of Z, and what you're left with is your probability X. So that's equation 17.1. You can also reformulate this if you use the definition of conditional probability. And so you can formulate this instead of with the joint distribution with the conditional distribution. The probability of X given Z times the probability of Z is what you integrate instead of the joint distribution. You're just, substituting for that. So there's going to be a lot of probability in here. Hopefully, for those of you who are pretty strong with your statistics, you'll be able to follow all of this. And if you're not, hopefully at least the big picture will make sense, even if you're not necessarily, there's going to be a whole lot of conditional probability distributions in this discussion today. All right, so that's the idea now that, okay, we have this latent variable model, and maybe we'll have some latents again about the breed of cat, the color of fur, the color of eyes, long hair, short hair, things like that help us describe this cat. And from that, we can get to our distribution over X without directly having to do things like model at the pixel level. So let's start with the simplest of possible latent models. Most of you have probably seen a one-dimensional mixture of Gaussians. Okay, so what we can do is we can say our latent variable Z has n possible values. Okay, some small number, let's say 2 or 3 or something like that. And each of them has a probability scalar that we represent by lambda. And so if it's 3 of them, we have lambda 1, lambda 2, lambda 3. So maybe one of them's 0.2, one's 0.3, one's 0.5. They sum up to 1. All right. And so then basically what we could say, the probability that it's a given Z, that it's 1, 2, or 3, is fixed. But each of those, if Z is 2, then the probability of this X is going to be this normal distribution, this Gaussian distribution. We have a given mean and a given standard deviation. So the way you marginalize over Z, this is discrete, it's not continuous. So instead of integrals, just a sum, but you just add up the 3 different distributions in this case. Okay. And this is a very straightforward process. We're very familiar with Gaussians. If I have 3 of them, that's really not any much more complex than if I have just 1 of them, right? But from this diagram, what you can see is that if you look at the diagram B on the right, in the front part of it, there's this light blue, blue-green, whatever. This is a very complex looking distribution. Looks nothing like a Gaussian. It has 3 modes. Yet, by combining 3 individual Gaussians, we can very tightly approximate this particular distribution. Okay? So the idea is that starting with something very simple that's just a Gaussian, from it by composing multiple of them, we can describe something very complex. So that's the intuition to take away from this 1D example. But now what we want to do is we want to move into real world problems that are much higher dimensional than that. So in this chapter, we're going to talk about building one that's not only higher dimensional, but also it's nonlinear. Okay, so before we were just using a linear weight of our 3 Gaussians, right? So we're going to have our X, the data we care about, let's say, again, cat images, and our Z, our latent, are both continuous and they're both multivariate, high dimensional. We're going to start with a prior distribution on Z And to make it simple, we often choose something like a normally distributed prior on Z. All right. That's just going to make all the math down the road later easier. You don't have to choose something simple. You can choose something that's more expressive, but you pay a severe penalty on computation. So for the purpose of this chapter, we're only going to consider the simple case. So now in the next two bullets, basically, we're going to build a neural network. That's kind of what we do in this book. We build deep neural networks. Okay, we're going to call this one F. Okay, it has parameters phi, and you put in some values, and it's going to output some values. And in the next bullet, I'll sort of say what exactly it is that we're outputting and inputting and outputting. Okay, so basically what we want to do is, if you look in the equations down below, we want to have this conditional probability that we've talked about. The probability of X given Z and parameterized by our neural network parameters phi. Okay, if we can calculate that, then basically we will be able to integrate over Z and we'll be able to calculate our distribution X. That's the concept here. Okay, so essentially this likelihood, the probability of X given Z and our neural network parameters, is what we're going to use this neural network for. And we haven't said yet exactly how we're going to optimize this neural network or anything, but basically, right, we're going to want to find the best parameters phi for this neural network so that they're as close to the true likelihood as possible. At this point, we have not said anything about how we would know if it's close, how we will find these parameters. Okay, but that's the goal of this nonlinear model, is that we say we have a neural network that will be very complex and will model this distribution. Cool. So we just do that and now we're done, right? Well, hold your horses. So in the 1D mixture of Gaussians, we summed up some simple Gaussians. And so you can imagine that for this nonlinear multivariate case, that basically we're building these little spherical Gaussians in high dimensions, these little balls, okay? And if you integrate continuously an infinite number of these, you can basically have any complex shape you want. So it's not a perfect analogy, but I thought about, like, you know, this thing in art where they did like pointillism, right? And so it's not exactly the same thing. They're not Gaussians, but the idea is that you can, from a bunch of different points, you can actually make up a picture. You can make up something, you know, much more interesting, much more complex. And so it's the same idea here. In this case, though, we saw a somewhat interpretable picture of 1D Gaussians. Now we're talking about high-dimensional spherical Gaussians. But if you build up enough of them, you can basically have whatever you want. So here's an image that's just two-dimensional, so it's a little bit easier to sort of understand what's going on. So our latent in this case is just one-dimensional. Okay, for simplicity, Z is just 1D. We're to pick a number you see on the left. You know, most of the time Z is going to be between -2 and 2. Okay, we run Z through this neural network, and the neural network is going to tell us what the mean should be. And so then we're going to sample a Gaussian with that mean, and that looks like sort of the thing in the middle. Just we get this sort of spherical hotspot of probability, and where brighter is high probability, dark is low probability. And so it fades the farther away you get from the center of the circle, the center of the sphere. If you had only one of these, you can only model something that's spherical. But the good thing is, for different values of Z, the neural network outputs a different mean, and so you have different spots. And so you can imagine that you could model a distribution that's this horseshoe shape, this upside down U shape in 2 dimensions. That looks absolutely nothing like a 2D Gaussian. Yet you can model it using this technique, because you're not using one 2D Gaussian, you're using an infinite series of them that you're summing up and averaging out. And so in this case, this is our technique. So you see the if you can read it, the bottom of the box on the right C, it says we're doing an integral of our probability of x given z multiplied, we're integrating out over probability of z. And so then if you drew a whole bunch of samples and you averaged them and you plotted that, it would look like the diagram C on the right. Okay. If you drew a bunch of samples for one z, then it would just look like B in the middle. It would just be a circle that fades as you get farther away. But when you draw lots of different values of z. So it's this composition of two things that you're sampling to get a z, and then you're sampling with the mean that the neural network tells you after you've done that. When you combine those two, hopefully you guys understand that you can now represent very complex things. Okay, so you have only two building blocks. You have a Gaussian z and you have a Gaussian likelihood. But the combination of those two actually lets you do very expressive, very complex things. So let me pause here. Any questions so far?
This is essentially for making shapes, like we have a blackboard and there's making blackboard, but there's it's just intensity, no color, anything.
Yeah, so the question is this for making shapes? So in the case of this example is only 2D. So then, yeah, really it's about 2D. But really what we're trying to do is we're modeling a probability distribution. So in this case, it would be like, I have a probability distribution. Where's my daughter? Okay, and the bright areas are going to be where it's extremely likely that she is. And the dark areas are where it's unlikely, okay? My daughter could be anywhere in San Diego, but there's gonna be a super bright spot at the house, a super bright spot at school, and then maybe there'll be some whatever. And so what I'm saying is that multimodal, very complex distribution can be modeled by this technique, even though we are only using two tools, a Gaussian for Z and a Gaussian for once you've picked your mean. And so the idea is that you have to composite a lot of these in order to get something complex.
So we're not drawing cats here, right?
So this is 2D, but if you got it up to like, whatever, 10,000 dimensional, then you can basically do the probability of the pixel intensities, and then you will have a drawing of a cat. Yeah, great. What's that? Yes, yes. You can do color channels, you can do. Yes, and I like to use images as an example just because they're fun to look at, and we've seen a lot of examples. But this technique really applies to anything that you want to estimate. So you could be estimating, I don't know, stock prices. You could be estimating runners, finishing times for races, housing prices, whatever. But the idea is that you have some random variable that's very complex, and you're trying to estimate it.
Yeah, can I just ask a question?
Please.
Yeah, thanks a lot. I'm new here, so I'm Galen. Thank you very much for presenting. And I don't know how, what the normal format of these presentations is, but I'm learning. When I was, sorry if there's an echo, by the way, I'm in a little room. When I was reading about, I had to refresh my memory about these variational autoencoders, but I found it very helpful to look at the kind of picture of the network and then to think of, and maybe this is too basic for some people, I'm not sure, but maybe that would be useful also. But perhaps you guys are more advanced and that's not necessary. But I think that the way I just wanted to make the point briefly that the way these types of things work is you basically take high dimensional data, you shove it through a network where you have a layer that reduces the dimensionality, and then you expand back out to the original size of the data, and that way you kind of trick your system into a lower dimensional representation, which I guess is what you were saying earlier about how autoencoders work generally. And then it just so happens that in these particular autoencoders, we force them to represent the mean and the standard deviation, which allows you to get this continuous representation that you were talking about earlier. So maybe it's helpful. I just wanted to mention that because maybe people get a little lost sometimes in the details. But
Yeah.
thank you. This is very interesting.
Yeah, thanks. Yeah, and the if you're trying to follow sort of the more formal mathy side, the important thing to understand is in a regular autoencoder, I'm just trying to compress information about the image. Okay. Um, in this case, I'm not just compressing the information about the image. I'm compressing the information about the image and a latent variable z that we're throwing into the mix. So what we are truly building in the middle is a probability distribution of x given z. So it's this likelihood, this conditional distribution is what we're building. And so that's why these initial slides, because we're throwing a wrinkle in here. We're not just um, um, building a distribution just of x.
Okay, okay, that's helpful. That's very helpful. Now
Yeah.
I think I understand a lot better. Okay.
Yeah. So at first, it might seem like, well, all you've done now is make the problem even harder because you've thrown in another thing, that this extra z. But as is the case sometimes, it turns out that if you reformulate the problem, even if you make the problem initially a little bit more complex, you can make it complex in a very specific way that it has some nice decompositions. And that's basically what we're doing here, is that we're making it more complex in a very specific way because it ends up being convenient. There's zillions of other ways in which we could have modeled a composite distribution of x and more stuff that would have been not helpful. That would have just made the problem even harder and even more intractable. But in this case, it's just because we're going to choose something super convenient. Let's see. There's a question in the chat. Any intuition for using Gaussian? And so I'm not a super strong statistician. The reason we choose Gaussians is because they're super convenient. We have lots of closed form equations for things that we can do with Gaussians, and you'll see on like the whatever fourth to last slide or something like that. We're going to get to this place where we need the KL divergence between the prior that we've chosen up top here, this prior on Z, and something else that we've built. And when they're both Gaussians, there's a nice closed form equation for the KL divergence between two Gaussian distributions, and that makes it computation not only tractable but also very fast. And ultimately, what we'll see in the conclusion is that we will be limited by choosing such simple distributions. So if you build a VAE with no other bells and whistles, and you do celebrity pictures, we'll see some slides. The pictures are kind of lousy. So you need further enhancements that add more expressivity, more complexity. But the basic technique, at least, is what we will cover here with these assumptions. All right, great. So hopefully, again, either you are mathy enough that you're fully with us, or you're not mathy, but you just get the general gist that we're going to do this different distribution other than just the data distribution, and that we can model anything complex. We can model more than just super simple things. Okay. Yes, the average height of humans is probably like a Gaussian distribution. But we want to model something like cat pictures, and that's just high dimensional and way, way, way more complex than that. All right. So how do we train this nonlinear latent variable model that we just described, where, again, we have a neural network that is predicting the mean of this conditional distribution, this likelihood? So we'd like to just pick the best parameters that maximize the log likelihood over our training set. And so if we plug in the formulas for this is a normal distribution, then basically what you can see is here's our conditional distribution. The output of our neural network is F, and we're using that as the mean. We're using sigma, and we're using spherical covariance. If you know what that means, don't worry about it if you don't. And then we're multiplying that by our original distribution Z, which is also Gaussian, which is also normal. We're also using spherical covariance for this. Yeah, so we just solve equation 17.9, right? No, this is computationally intractable. All right. So what we need to do is we need to find something that is more computationally friendly that's similar to this. And it turns out that we can derive a lower bound for this likelihood. And not only that, but we can get this lower bound very, very close to the actual likelihood. So, so this lower bound, we're going to call the evidence lower bound. So there's this term that appears in variational inference, which is the ELBO. Okay, it's our evidence lower bound. And in order to explain the evidence lower bound, we're going to first pause and get another tool in our tool chest, which is Jensen's inequality. All right, just checking the chat here. Okay, so let's talk about Jensen's inequality, okay? So Jensen's inequality says if you have a concave function, so this is curved downward. So imagine y equals negative x squared, something like that, okay? If it's concave everywhere, then that means that the second derivative is always negative, all right? The output of this function, and then we just have some function, okay? This concave function. The output of the function, if you evaluate it on a single valued expectation over some set of data, is always going to be greater than or equal to the expectation of the function on all of that data. That's kind of like a bunch of word soup. So I personally find it easier to read the equation here. Okay, so if our function is called g, then running g on a single number, which is the expectation of y, is always going to give you a bigger answer or equal than if you ran g individually over all your possible y's and then did the expectation over that. All right. In particular, logarithm is a concave function. Second derivative is always negative. And expanding log into the formula above, and also expanding that expectation is an integral. So the expectation of blah is the integral of blah times the probability, okay? So if we plug both of those things in, we get equation 1712. So you can see where it says, if you integrate over all the possible values of y, if you integrate y, and then you take the log, that's going to give you a bigger number if you take the log of y and you integrate over all the possible values of y. On the next slide, we'll get pictorial, and I personally find it's easier to think of it pictorially than it is to just think of it in terms of equations. It turns out also, by the way, that there's a whole family of things you can prove related to this. And one of the things is you can replace, here we're doing the probability times y. You can just do a function h of y, and Jensen's inequality still holds. That's 1713. All right, so let's look at a picture. That should be a lot better. All right, so the book has a diagram, but I didn't like the diagram in the book that well. So, so let's just start with a much simpler example. Let's just start with 2-point masses. And so these are the little brown rectangles that I drew on the left and right. Okay, so just imagine you have 50% of your probability on the left and 50% of your probability on the right at a single point. Okay, so then what is the expectation of y? Well, it's just going to be the halfway point. It's just going to be the average of those two numbers. Okay, so this is not a complicated distribution. It's just 2 points. So the expected value for y is the middle. It's this vertical dotted line. Okay, what is the log of that? Well, that's just the point on the curve up top. That's in red. What happens if you take the log and then you take the expected value? Well, the log of those is the two green dots, the green dot in the lower left corner and the green dot in the upper right-hand corner. And if we average those, then once again, it's just the midpoint, which is the blue dot in the middle. You can see quite clearly the red dot is quite a bit more than the blue dot, okay? If instead of the 2-point masses being 50-50, you had any sort of spread, 10-90, 90-10, whatever, then basically you will just wind up with some blue dot that's on this line that connects the two green dots. And all of those points on this line are clearly below the log curve, okay? And then on the next slide, as we get a little bit more complicated, if you allow probability to be not just at the two endpoints, but in the middle, then what you can do is you can wind up with a point somewhere in the gray shaded area instead of just on that line. Okay, the line is what you get when you only use, stuff from the two ends. And so an easy way to think about, for me to think about the gray shaded area is, let's say we went from just having 2-point masses to 4-point masses. Well, what I could do is I could just take 2 of the points at a time, average them using exactly this rule, saying that I'm going to get something below the curve. And then if I average those 2 things that are already below the curve, I'm still going to be way below the curve. And so for me, the intuition is you can start with 2 points. You can get to any number of points just by continuing to average them. And then you can just imagine in the limit, if I have an infinite number of points that I weight, I'm just going to wind up somewhere in this gray area. All right. So if this picture works for you, good. If you prefer the author's diagram, that's fine also. So here he shows at the bottom, instead of my 2-point masses at the end, a nice smooth bell-looking kind of a distribution over here. And so the expectation you can see falls in the middle still. And what he's trying to show is that because of the shape of the logarithm function, on the left you see this, again, the blue or blue-green teal, I don't know what to call this color. The shape of the probability of the log of y does not look the same as the shape of the probability of y because log is a nonlinear function, right? And you can see like which way it got pushed, okay? So this is why this higher line is the log of the expectation, and this lower line is the expectation of the log. So if we, all right, any questions? All right, so if we have this, again, hopefully you've got some intuition, but the main thing is you need to know that this is true. And if you flip the signs, then you can do, for convex functions, you can do the reverse. You flip your less than equal to a, greater than equal. So if we have this, what we're gonna see on the next slide is we're gonna have a situation where we have log likelihood and we're gonna have a log. So if we frame that as an expectation, then basically we can say, there's a relationship between the expectation of this log likelihood versus the log of the expectation. So that's why we want Jensen's inequality. So how we do it is we're going to introduce a new probability distribution Q. We haven't said why Q, we haven't said what it is, but if you just take Q in the numerator and Q in the denominator, we're multiplying by 1, okay? And so you can rewrite our equation to look like 1714, where we purposefully, for understanding purposes, put the 1Q that's in the numerator on the left, and then we put the other one in the denominator. And so when we integrate over Q times something, okay, that's an expectation. So anytime you integrate over the probability of something, that's an expectation. So now we've just turned equation 714 into the log of an expectation. And so what we can say down below in equation 1715 is that the log of the expectation is going to be greater than the expectation of the log. So I've moved the log from outside the integral to moving the log inside the integral. And this means that this thing in the orange dotted box is guaranteed to be less than or equal to our true value, which is on the left. And because this thing in the brackets, the probability over Q, in Bayes' rule, that's called the evidence. Therefore, this got the nickname the evidence lower bound. So it's not apparent at this moment that this is more convenient. However, soon it'll become apparent that the thing on the right side is more convenient for us to work with than the thing on the left side, okay? And we've got this Q now. Well, it's like, well, we've actually made the problem harder in the sense that we now need to pick a good Q. Okay. But if you pick a good Q, what can happen is that this greater than or equal will be super, super, super close to equal. And if it's super close to equal, if it's approximately equal, then that means that for all intents and purposes, the thing on the orange box can freely be used instead of the thing on the left. So now instead of maximum likelihood, we can do maximum ELBO, and we've solved our original problem. All right. So what is our function Q? Let's pick something simple. Let's pick a Gaussian. Let's parameterize it by some thetas. And so then basically we're then going to have the ELBO at the bottom of the slide, equation 1716. We can write it now with these extra thetas in there. So we have more parameters now. So it's the same thing as above, but we're just writing it more formally, saying that what Q looks like does depend on our parameters theta. So it's Q of Z given theta. Okay. So there's a lot of math formality, but essentially all we're saying is we now have a way where if we pick a good Q, we can get a lower bound that's essentially, for all intents and purposes, approximately equal to the likelihood that we wanted in the first place. What's going to happen working with this ELBO, if you look at this diagram from the book, is that when we change our network parameters for what Q we're going to use, it's going to give us different curves. So we can have the orangey brown curve, or we can have the blue curve. And so we can move this curve up by picking better thetas. Our original problem was parameterized, if you remember, by a neural network with parameters phi. Okay. And what that does is that moves you along any one given curve. So on the left, it shows you if you pick better thetas, you get a higher curve. And on the right, on diagram B, it shows that if you pick better phi, then you move to a higher point on any given curve. And so ultimately, our goal is to get this little curve that's below super close to the tippy top of, over here, super close to the tippy top of our actual log likelihood, and to pick the point on the curve that's also at the tippy top of that curve. And if we do both of those things, then basically we will have maximized our likelihood. And so then we will have solved maximum likelihood in order to get us the best parameterized network. There's a little more math that we are going to take advantage of. So not going through the derivations, you can look in the book, okay? In section 17.4.1, they show that just simply by like using simple rules of probability that like, you know, the conditional probability and the joint probability are related by, you multiply by this, divide by that, whatever. You can move things around, and then eventually you will get an integration over this multiplication, and that's the definition of KL divergence. So for those of you who aren't familiar with KL divergence, it's loosely, okay, you can think of it as a distance function for probability distributions. So probability distributions that have very similar shape, that have mass in the same places, are going to have a KL divergence very close to 0. And if you had like a unimodal distribution with a big mode in the middle and a bimodal with modes in the end, then that distribution is going to have an extremely large KL divergence. Technically speaking, it is not a distance metric. One of the problems with KL divergence is it's not symmetric. So if you have probability distributions P and Q, the KL between P and Q does not give you the same value as the KL between Q and P. It's not commutative. Okay, so it's not a distance function technically, but loosely you can think of it as that. And so this top equation basically says that, oh, okay, how much our ELBO differs from the actual likelihood that we want, which is the first term, is this KL divergence. So if we can get Q to be really, really, really close to the probability of Z given X, then that means that this ELBO will be super tight. It'll be just what we want. So that's one way to think about it, is that's how we know how we have a really, really good Q. Okay. The bottom half also shows us that you can juggle around all the terms, okay? And you'll have a different KL divergence. If you look closely, you'll see that the bottom one, the right-hand side of the KL divergence, is not the probability of z given x, it's the prior. It's just the probability of z, okay? This expression on the left, people call this the reconstruction loss because if Q and your data X agree, then the likelihoods in here are going to be very, very high, close to 1, okay? And so basically this term on the left is going to be low. You're going to get penalized whenever your Q of Z does not match the data. And this thing on the right, it says, how much does Q match your prior? So this is the exact same formula. They've just juggled around the terms. And so they say another way you can think about this is that it's the reconstruction loss, the match with the data, plus how far your Q differs from your prior, okay? The top term is a little bit more intuitive, but the bottom term, it turns out, is very amenable for computation. So we're going to use 1718 for the equation 17.18, and that's what we're actually going to plug in and do for building our actual variational autoencoder. Getting close, but we still need a couple more tools in our tool belt. So how do you pick a good Q? Well, generally speaking, what you're going to do when you need to pick something is you build a neural network and you run back propagation to estimate it. So we call this a variational approximation. We're going to choose a family. Once again, for the simplest form of variational inference, we're going to choose a multivariate Gaussian because that's the simplest, easiest probability distribution to use. And so our neural network here is going to be picking the mean and it's multivariate, so it's covariance, but you can, in univariate terms, it'd be like the mean and the standard deviation. But so the mean and the covariance for our distribution Q, okay? The other thing we can say now is we're now straying from the realm of just theoretical math to an empirical problem. I have a data set of 100,000 cat images. And what I want to do is I want to build a good model for this set of 100,000 images. So really what we can say is it's not an arbitrary theta, but it's a theta that's dependent on our data set X. So now we've slightly rewritten it to say, instead of just Q of Z given theta, we're now saying Q of Z given both X and theta. All right. And so what happens is theta is the parameters to your neural network. And then you plug an X into your neural network and it pops out a recommended mean and covariance. Okay. You can do this for one data point. You can do it for multiple data points. But in the simplest case, if you just throw in one single cat picture, this neural network will output what it thinks the mean and what it thinks the covariance for your Q distribution should be. Okay. By running backprop, we can get our theta parameters to be better, and so we can pick a really good Q. And we're just going to run this over our training data. All right, so we're pretty close now to building our variational autoencoder. So what do we want to do? We want to compute this latest form of our ELBO. And so this equation 1721, it's got a lot of letters and symbols and whatever, but it's just the same equation. We've just plugged in the fact that like Q depends on both X and theta and whatnot. This left-hand term, once again, this is an intractable integral. We cannot solve this. However, what we can do is we can look at this and we can say, oh, inside of this, it's really the log probability of X given Z. And we have all these data points. So if we sample a bunch of data points, we'll get a reasonable estimate for what this is. And the simplest estimate is just the single point estimate. And so what you see in the second equation there, 17.23, is that we've just basically dropped the integral. And we've said that, hey, we're basically just going to use this likelihood. This thing on the right, this KL divergence between our probability distribution Q and our prior, this is the place that got mentioned earlier when we were talking about Y Gaussians. We've said Q's multivariate Gaussian. We said our prior is Gaussian. This KL divergence term on the right has a closed form formula and is very fast to compute. So the book has the formula. I didn't even bother pasting the formula in here. The only thing you need to know is that if you know the mean and covariance for your distributions, boom, you can just drop it in. So this means that we now have an equation 1723. Given a set of data points X, we have a way of estimating, calculating this ELBO. So going back, this all started with we're trying to maximize the likelihood of our data. In machine learning, we're used to doing minimization problems on our loss function. So what we're going to do is we're going to use -1 times the ELBO to be our loss function, okay? And we're going to try and minimize that. So that technically is maximizing the ELBO, right? So maximum ELBO means maximum likelihood. All right, to compute this ELBO for a single data point, what do? So we run that data point through the second neural network I talked about, and that gives us the mean and covariance for our distribution Q. That's a distribution. That is not a single value. So we now sample from that distribution. We pull a random draw from that distribution Q. This is what we're calling Z star in the formulas. Using that Z star, we now can calculate the ELBO, and we can do I said that KL divergence closed form on all of that. We can now completely calculate this. It probably makes more sense, and there was the suggestion, thank you, I think it was Galen earlier. It's probably a lot easier to see in a diagram. And so I really struggled with, do we show the diagram earlier, or do we just wait, like in the book, to show it at the very end? But so here's the diagram. I find the diagram a lot easier to think about conceptually. So the encoder is the network that I talked about more recently. This is the thing that you plug in a data point, and it predicts a mean and covariance of a distribution. You can sample from that distribution. The right-hand side, we're going to call that the decoder. And basically, once you've sampled from that distribution, you plug it in there, and you get this likelihood. With these two halves, the part from the left, the part from the right, you can calculate your ELBO. Is that a question?
Yes. So how do you decide, with how to, because when you're, minimizing your loss, it's a combination of both the KL, or I don't remember the term, but
Yep.
How different your prior and posterior distributions are, and the, I guess, difference in pixels between your input and output. How do you decide how much you care about one versus the other, like that hyperparameter?
Yeah. So in the original VAE, there's a mathy reason why those two terms are there, and so they're just weighted vanilla like that, one each. But it's a great question because in principle you could put your finger on the scale and say care about one of them a little more than the other or whatever. It turns out that if you are using as your prior something with spherical covariance, okay, so no interaction between the different dimensions, then emphasizing that particular term causes your Q to look more spherical, okay? And there's a slide later on. So there's a architecture called the beta VAE, and the beta VAE is nice because it tends to give you more disentangled latents. So if you're doing cat pictures, you might have where you're like, hey, I can actually see floating point number 3 tells me the fur color, and floating point number 7 tells me the length of the tail, and floating point number 12 tells me how long the hair is. We really like that when we have human interpretable latents, as opposed to you could just take the exact same information, rotate it, and it's completely like unobvious to us because we don't know sort of where the bases are. So in fact, your question, so that's one of the tricks they did was they weighted that second term a little heavier, and they found it tended to push the model towards nice interpretable latents. in the original math, there's a reason why that they're 1 and 1 is because this is theoretically an exact estimate of the likelihood with the ELBO. All right, I'm gonna keep going because I see that my laptop's on power save and I don't know where the nearest plug is. So let me see if I can just quickly finish. We're just about done. So in this diagram, you can see now why people call it an autoencoder, because you've got this thing on the left that you pump data into and you get something small out of it. And on the right, you put something small into it and you get out something so that you basically can reconstruct your original data. But it is, once again, like I said at the beginning, very different from a traditional autoencoder, because what you have in the middle is you have a distribution. You sample from this distribution, and for a single given input, X on the left here, you can sample with different random number seeds as many times as you want, and you'll get completely different cats. Now, obviously, if you're training this, then the parameters will change and you'll get different looking things. But even with frozen parameters, you can put the same input in and you'll get bunches and bunches of different outputs out. Eventually, what you'll do is with most autoencoders, what you do is you throw away the encoder. You're like, I use that for training purposes. I'm just going to throw that away. I just want the decoder where I just randomly pick a latent and then I generate a bunch of different images. Okay, so one more time showing you here, what we're doing is we're changing our theta parameters to move our Q curve up, and we're changing our phi parameters to pick what point on the curve. And so hopefully we keep getting closer and closer and closer to the tippy top here. And yeah, there's the possibility that, like, well, moving phi in this direction was a good idea for where the curve used to be, but you just moved the curve on me, so it's not. So it is possible that you're not just going to make perfect straight progress towards there, because every time you change one of them, it sort of might be messing up the other one a little bit. But eventually you hope that you get, sort of close to the top and you're making small changes. And then once you get near the right, then hopefully you'll just sort of like converge to, your local minimum, and you'll get the best possible parameters. So the one last thing that we need is, we said in the middle of this diagram here, this blue is we sample from our distribution Q. There is no gradient for sampling, so you cannot run back propagation. Okay, but we can take advantage of a simple thing that if you sample from a unit Gaussian and you just multiply it by the covariance and you add the mean, then that's the same thing as sampling from. And technically speaking, there's a square root in there, whatever. But so basically what you do is you reformulate it so that you do this multiplication by the covariance and you add the mean in. And if you do that, you can back propagate through the value of your covariance, and you can back propagate through the value of your mean, which is what you want. The sampling itself, you cannot back propagate through, but that's okay because that sampling is fixed. It's always unit Gaussian, so you don't need any learning. There's no need. So this reparameterization trick is used in a number of different ML models. All right. I saw there's a comment in the chat. I don't think it's a question, but please let me know if there's a specific question before my computer battery dies. Okay. The author then at the end of the chapter talks about a few different ways you can use VAEs. You can do sample probability. It's not really easy if you just, yes, thank you, it's running low. If you just directly try and pull out the probabilities, what's going to happen